Hello, good morning. You should see the desktop now and should be able to hear me. Does that seem right?
Yeah.
Okay, good,
Yep.
thanks. Okay. Um, okay. All right. First, I changed the syllabus. I mean, so you may have noticed I put this up last night. Uh, there was supposed to be an exam this week, but I haven't been paying attention and it hasn't been, we weren't really ready for it. So I changed the exam. It was supposed to be this Wednesday to push it to after spring break. Since spring break is coming up, I pushed it to well after spring break. So that moves it from instead of this Wednesday, next week spring break. Didn't want to have it right after coming back from spring break. That's not such a great thing. So that week there. So that'll be not the week after spring break, the week after that. Okay, so that gives plenty of time. And you don't come back from spring break and have an exam right away either. Okay, so that's the exam. And then there's a bunch of, if you look at this document here, okay, it tells you the exam is over these chapters. Okay, there's the chapters, the chapters on scheduling, on processes. So it's on the chapters on processes, and then the stuff we did in C. Yeah, so some chapters from the books on C. So that's references to this book here. Okay. Okay. So references to the chapters in this book on C, and also there's also this other book on C that has some good chapters in it also. So the more advanced parts of C, specifically arrays and pointers and structs. Okay, the kind of stuff that we really need in this class. So not for loops, while loops, and if statements, but arrays, pointers, and struts, the kind of things, and also parameters. But it's also a little bit about functions, but that's pointers to functions and yeah. So how these things get used in functions. Okay,
Excuse me,
so
Professor, where did you link that book?
pardon me.
Where did you link that text?
Well, it's linked in the course website, and it's linked right here.
Okay, thank you.
See, it's right there, and it's in the syllabus. It's this book right here, and the other one is this book. Well, the other one's not in the syllabus, but it's this book right here. And the other one, I didn't link to it in the syllabus because it disappeared off the internet for a little while. Remember, I had to actually copy it to my server, which is illegal. But I actually, this other book, it just disappeared one day from the internet. But I happen to have had a copy of it on my computer, so I just put it up on the server. So it's up on there. Okay. So it's not in the syllabus, but it's been part of the reading assignments. Okay. So go back here. There were, see, there's chapter 6 and chapter 7. Those are the two chapters you need to know, chapter 6 and 7 from that book. Okay. So they were part of the reading assignments going back in the course. Okay. And then, okay, so this is what the exam, that's the material from the exam. And then there's a bunch of questions that are good sample problems for you to from reading this stuff, you should be able to answer these questions here. Actually, some of these questions are not in that material. Like this question here is about homework programming assignment 1, where you had to use a command line. In programming assignment 1, you were writing a filter. And this is a question about filters, about command lines and filters. And the references for here are down here. So for example, here's where Microsoft explains how their command shell works, how their command line works. So it tells you some of the information you need to understand this problem here. And there's another page here where Microsoft explains, see, they explain what those symbols mean. If you go like over here, see there's all these little symbols, greater than, less than, we call this pipe. Okay, here's the page that explains, whoops, here's explained that, what does that mean? What does that mean? What does that mean? What does that mean? So that's where Microsoft explains them. Okay, and there's another page from another website that also explains them. Okay, see that symbol, that symbol, that one. We use those in the homework assignments, And here we didn't use the ampersand, but these problems ask you to figure out what does the ampersand mean in a command line. Okay, so this problem is actually really reviewing stuff from that programming assignment. So right there is the material that you would read to understand those. And those were references that came with the program assignment. If you go back and look with the program assignment, there were links to these references back then too. Okay, so some of the questions are referenced by this. Those are the first few questions about command lines. And then the rest of it is about processes, and it's about this. And then there's questions about C that are from here. Down towards the end, see, there starts to be questions about C. Okay, so these are the end. These are questions about C at the end. In the middle are questions about processes. These are questions about processes. And at the beginning, there's questions about command lines. So the first several questions, the first 10 or so questions are about command lines. Okay, and if you have, oh, now these are review problems for the exam. They're not the exam. So if you have questions about these, ask about them or work with people and talk to people about them. Make sure you can understand what's it, because this is what the course is really about. These kinds of being able to answer these kinds of questions is what the course is really about. So if you have questions about them, ask. Now, the one thing I'm not going to do is put up an answer key. I won't put up an answer key because I don't want anybody just memorizing these answers. So the goal is that you would figure them out. So read through these and understand what they're asking and solve the problems. But if you have questions about them, feel free to ask. And if you want to show me an answer and ask if it's the right answer, I'll tell you whether it is or not. So you can show me an answer. You can ask me a question about an answer. You can ask me a question about the question. You can talk to people about them. This isn't the exam. This is practice. So work on these. Okay. So and ask questions about them. Okay. So that's the okay. So that's where we are with the course. So the exam will be, that puts it 3 weeks from Wednesday. Remember, that puts the exam quite a ways away. It puts it 3 weeks from Wednesday. Okay, so it gives plenty of time. Okay, and let's see. Close that. Okay. All right. Then what I want to do today is finish talking about system calls. Now, we started doing this uh, last Wednesday, and actually I goofed up. I did the examples in the wrong order, and I didn't have time to prepare, and I kind of just somehow accidentally did the two exact. I'll show you what I mean, but I did them in the wrong order. And while we were doing it, I was wondering why these numbers don't look right to me, and it's because I was doing the examples in the wrong order. So we're going to do them again in the right order today, and we'll see the numbers are going to be way more dramatic. They were supposed to be really dramatic, and they weren't the other day. And I was trying to remember what's going wrong. And then I realized I did the examples in the wrong order. Okay, so I'm going to do the system call examples in the right order. And then we'll see a really dramatic shift in something that's real important. This is a really important example. This is one of the secrets of programming. This example that we're going to do is actually something that way too many programmers don't know. Now, it's the kind of stuff that if you're, let me give you an example. Suppose you get a job and you write JavaScript for web pages. And so all you're doing is writing JavaScript. None of this matters to you because you're running JavaScript in a browser. But on the other hand, suppose you get a job where you're at the other end of a web app. You're doing what people call back-end stuff. You're managing the database servers. You're managing the web servers. You're writing the code that interacts with the database and web servers. Then you care about this a lot. The example we're going to do today, you care about it. It's actually everything you care about is in this example today. I mean, it's why your programs are slow or not slow. It's a big part of why people end up with slow programs when they don't understand what's going on. Okay, so what we're going to talk about today, it's something. JavaScript is too abstract a language. It runs too far away from the operating system because JavaScript runs in a browser, then the browser runs on top of the desktop. The JavaScript code really runs a great distance away from the operating system. But web servers, database servers, backend code, node code, all that runs right on top of the operating system. And then you care about what these examples are going to do. And to people who do that kind of programming, the more low-level programming, what people these days call the back-end programming, They care a lot about this. This is one real important idea to understand. Okay, so remember now the example we did was this one, where we're reading 1 byte at a time from a file. Okay, now so we want to read a file and count how many bytes are in it. So we read the file 1 byte at a time and count. And I remember the way this works. This function says read into this buffer this many things of that size. Now the size is 1 byte and the buffer size is 1. So we're reading 1 byte at a time into here. If you ask read to read 1,000 bytes, it might not find 1,000 bytes. So it tells you how many bytes it actually found here. So if we're asking it to read 1 byte, this thing's either going to be 1 because it found 1 byte or 0 because it got to the end of file. If it found 1 byte, we count it. Okay. If it didn't find any bytes, we drop out of the loop because we got end of file. Okay. So read 1 byte at a time into our buffer from the file. So we're telling this thing fetch up. Now it doesn't really fetch it from the file. That's what programmers think of. They think this thing goes out and gets 1 byte from the file and puts it in my buffer. Then it goes out and gets one more byte from the file and puts it in my buffer. Well, it doesn't really go get 1 byte from the file. So we'll talk a little bit about exactly what it does. It goes to the operating system and asks the operating system to go get 1 byte from the file. Okay, but it's getting 1 byte at a time. Now we have this other version that's a Windows program. Okay, this one is a C program. This one's a Windows program. See, it needs the windows.h include file. And we're switching now from a C library function to a Windows library function. Okay, now over here, what's happening is printf and fread are both in standard IO. They're both C functions. So the fread is from that include file and printf is from that include file. So these are part of the C language. Now we still need this header file because we're using printf. We could use read, but instead we're going to use read file, which is part of the Windows library, the Windows operating system. So we're not going to use C's read, we're going to use Windows read. Okay, so essentially we kind of bypass C and go straight to the Windows operating system. We still need that include file because we're still using printf. If you comment out that include file, the compiler will tell you I can't find printf because you didn't include it. Now there's a third version in here that's a Unix version that'll compile under Linux. And you can see the difference where this one wants a Windows header file. This one wants a Unix header file. See, Unix standard library. Okay, so that's a Unix standard header file. Now, I'm still using printf, so I need the C IO library because I'm using printf, but now I'm using this read function, which is from that library. This library is part of Linux. This library is part of Windows. Now, this one's purely C because C does have a read. Now, the point is that this C library function, that C library function calls this function inside of it. What you don't know is that inside this function is a call on Windows. If you're on a Windows computer, this function calls that function. On the other hand, if you're on a Linux computer, this function actually calls this one. Okay, so on on whatever operating system you are, if you have a C file like this, it'll run on any operating system, but fread has to turn into the read function of that operating system. So that fread turns into this one on Windows, and that fread turns into this one on Linux. So if you want, you can bypass that one. But if you bypass that one and you go to this one or this one, now your program only runs on one operating system. That program only runs on Windows. That only runs on Linux. That cuts off a lot of your market. So the whole point of this world is to have a C library that's platform independent. So you can write as much code as possible that will compile and run on all operating systems. So that means Windows, Linux, Android, Apple. This will compile and run on every operating system that supports the C language. So this file has most everything you need is in there. Okay. But everything that's in there ends up calling things from in there on Windows, and everything from in there ends up calling things from in there on Linux. Okay. But you don't want to use this and you don't want to use this unless you have a good reason to, because if you use this library, your program won't run on Linux. If you use this library, your program won't run on Windows. Okay, this library is part of Mac because a Mac machine actually is a form of Unix. It's not a form of Linux, it's a form of Unix, but that a program written for this will run on a Mac because the Mac is a Unix machine. Okay, so but this is the safer way to go. Okay, now these functions are more or less alike. Right now we're going to compare the Windows one to the C one. Okay, so we're not going to play with the Linux one. Now they act very similar. The C one says read from that file into that buffer. Well, I'm sorry, into that buffer. See, C is the buffer. Okay, so read, F stands for file, read from that file into that buffer. And then this tells it how much to read. I want one byte of size 1. Okay, so read from here into here. And if you look at the Windows one, it's read from here. That's the thing that says it's the standard in. That's the input file. Read from there into here. This is how much to read. Now, remember this one says, oh, and this is how much I found. You might ask for 1 byte, but you may find 0. So it gives you this output that tells you the return value. Well, Windows tends to use output as error tests, so they use n as an out parameter. Notice that the n here, which is the return value, this is why we talked a lot about differences between in and out parameters. Here's a good example of the C library decided to use the return value to tell you how many bytes it counted. The C library decided to use an out parameter to say how many bytes it counted. Okay, see that ampersand there is the way we say it's an out parameter. You have this variable, but then you point at it so that this function can fill it in, what we mean by an out parameter. So if you ask it to read 1,000 bytes and only finds 557, this thing will tell you how many it found. Okay, we don't care about this parameter, so it's just an optional parameter. So read from here into here. I'm sorry, from here into here. Read from here into here this many bytes, and then it tells you how many bytes it actually found. Read from here into here this much, and let me know how much you actually found. Whereas here it's read from here into here and let me know how much you found. Okay, there's the return. Okay, so they're doing the same thing. And if you look at if you look at the Linux one, it's got the same structure. Well, the same idea. Read from here into here this much, and tell me how much you actually found. Okay, read from this file into this buffer, this much stuff into the buffer, put that much into the buffer, but tell me how much you actually found with this return value. Okay, so they need to know 4 things: where to read from, where to put the data, how much data to get. They need to know 3 things: where's the data coming from, where's the data supposed to be put, and how much data do you want. So they all need to know, they need to be told 3 things. And then the function tells you back 1 thing. This is how much I found there. Because there could be, you might think there's going to be 1,000 bytes in the file, but the file only has 900 bytes in it. So just because you ask for 1,000 doesn't mean you get 1,000. Okay, so, and usually when you don't get as much as you ask for, that's the sign that you hit end of file, because hard drives are reliable. And that's not the case with network connections. A hard drive is reliable. If you ask a hard drive for 1,000 bytes, you'll get 1,000 bytes if it's there. Hard drives don't fail. So the only way you don't get as much as you ask for is because you got end of file. If this thing's reading from a network connection, then it's way more complicated, because network connections fail all the time. So if you ask for 1,000 bytes from a web server and you don't get back 1,000 bytes, that doesn't mean you've hit the end of file. There's lots of reasons why you don't get back as much as you asked for. So when you're reading from a network connection, things are way more complicated. But hard drives are considered reliable. So if you ask for n and get less than n, it's taken to mean you hit the end of file. Okay, so see, okay, so all these loop until they get to some, they loop until, like this one loops while it's, see, I'm asking for 1 byte. So I this really should have been less than n, because in general, if I change n to some other value, it could be, I might, yeah, but this one works. This one actually what happens is this one works okay, because suppose you ask for 1,000 bytes and you get 500, and then you ask for 1,000 bytes again, you'll get 0. So you'll do one more read past the end of file, which is considered fine. So if so, checking for 0 means I'll actually do one more read past the end of file. So if there's 500 bytes in the file and I ask for 1,000, I'll get back 500 here, which isn't 1,000. But then I'll loop and ask for 1,000 again. But then since I really hit the end of file, I'll get back 0 the second time, and then I drop out, which is considered a okay way to do it. So I could check for less than 0 here, or just check for equals 0. Okay, same over here. Yeah, here I'm checking that n is not here. Here I'm checking. I want to keep reading while I'm greater than 0. Okay, so again, I quit when I hit 0. As long as I got more than 0, I keep reading. Okay, as long as I got back something, I'll go ahead and do another read. So that's what this is saying. And you do it as an and. It's weird. See, it's weird. You call the function and you and its return value with this condition here. Okay, what that means is if this thing returns 0, that's failure. So you're actually doing 2 tests here. You're checking for a failure of the read, which means that something went wrong. Not that you hit end of file, but that something went really wrong, like the hard drive failed, which isn't very likely. So the left side of this and is checking that this thing's reporting failure, and this is checking that you're getting as many bytes as you want, that you got some bytes. As long as you got some bytes, go ahead and ask for more. Okay. This one doesn't have a failure mode. This one just says read, and then it tells you how many bytes it found. If it failed, it's just going to give you back 0. So 0 can mean here both I hit the end of file or something really bad, and I don't know. Yeah. So the trouble with this one is that the 0 return value can mean either failure or I hit the end of file. Microsoft chose to distinguish those. So this thing returning 0 means actually failure, and then you need an and here. The n is used to measure end of file. Okay, all right, but these functions are doing the same thing. They're reading, in this case, 1 byte at a time. We're reading 1 byte at a time. Okay, now there's a README in this folder with these guys that explains things. Okay, and it tells you what to do. So first create the text file. Create the text file that's going to be used for testing purposes. So create the text file. Well, first you have to download it. So double click on that and it'll, there, that downloaded this text file. Now make it larger. See, it starts off as 6 megabytes. So I want to make it 50 megabytes. So I make it 50 megabytes by copying it into itself over and over again. See, I copy it to, this idea of just doubling it in size from 6 to 12 to 24 to 48. So I just keep doubling it in size by see, I'm using that symbol that's in that that's part of the exam. What does that mean? That means list out this file, but redirect it to the end of itself. Okay, so list the file, all its data to standard out, but redirect standard out to the end of that file. So that appends the file to itself. It's a real common trick. That doubles the size of the file. So it doubles from 6 to 12 to 24 to 48. And now it's at, see, 49 megabytes, because it started out a little more than 6 megabytes, and it's doubled. Now it's not quite 50 megabytes. Okay, so that's my data file that I want to play with. Okay. After doubling, after downloading it and then doubling it, I want to compile my two programs. So here's the command line for compiling the programs. So I need a command line down here now. Compile one program. That one compiled the Windows version. And I can also, here's a command line for compiling the C version. Now, what we did last week was we only did the C version. I forgot to do we should have done the Windows version before the C version. And I started doing the C version before the Windows version. And I forgot it really matters. Yeah, I should have, I was supposed to do the Windows version before the C version. And everything makes a little bit more sense when we do it in that order. But I made the mistake of doing the C version first. Okay, so now we're going to do the Windows version and then compare it to the C version. That was what the goal was really to do. Okay, so now what we want to do is run the Windows version, have this program count the number of bytes in that file. Okay, the command you need is right there. I want to time how long it takes to run the Windows program with big text as its input. Notice I'm using this symbol again. Yeah, that's saying run this program with its standard input from that file. So this program is reading from that file, okay? And I want to time it. So I want to see how long it takes, okay? So run it. Now, it's going to take about 1.5 minutes. I ran it earlier today, and it'll really vary from machine to machine. So on your computer, it might take a different amount of time. Okay, now, while that's running, let's go and remind ourselves of a picture that we had last week. Okay, last week we drew a picture that went with this. Where is it? Okay. Now, this picture is not the picture. Well, this picture, I was talking about fread, but this is the picture of read file. So I got this kind of goofed up. Okay. This is actually the picture that belongs to the Windows version, not the C version. So I redrew this picture. Oh, let me get it off my, I'm gonna put it, I haven't put it up on the website, but I redrew it. Let me get the redrawn version and show it to you. Okay, so I've got this. I'll put it in here. Okay. I've got two versions of the picture now. One for fread, which is the C library function, and one for read file, which is the Windows library function. I want to compare these two pictures. Now, right now, I've got them pretty much looking exactly alike, but I haven't finished one of them. One of them's not finished. See, there's the two of them. There's the one that says fread. See, well, they're almost exactly the same. Okay, but we want to see that the fread, the picture should be different for it. I'm going to edit this picture in a minute and show you something that's interesting. Okay, so the picture we did last week was really for read file, but I drew it as if it was for fread. The fread picture is slightly different. Okay. Oh, program finished. It took almost 2 minutes. See, it took almost two. It took 1 minute and 57 seconds to run. Okay. All right. Now I'm going to run the C version. Okay. Now let's go back to the code. Remember, there's almost no difference here. Look at the code. Declare that buffer, declare those variables, declare that buffer, declare those variables, enter a while loop, enter a while loop. Now this one needs to open that handle. Okay, so you have to open standard input. Okay, so that's a little that's something you have to do in Windows. You don't have to do in C. In C, standard in is open for you automatically. In Windows, for some kind of weird reason, standard input handle is there, but then you have to turn it into another handle. It's just a weird, this is one of the Windows's weird little quirks. So you have to essentially open standard in. Okay, So that line of code is that's an extra little step there. Okay, that takes a billionth of a second to do that. Then you enter the while loop, and then you read 1 byte at a time into that buffer, and you read 1 byte at a time into that buffer, and you count the bytes. So very similar programs. Okay, now if I run the I just ran the Windows version. Here's the command line for running the Linux, the C version. Run the C version. Oh, it runs in 2 seconds. Okay. The Windows version took 120 seconds. This one took 2 seconds. Why is that loop 60 times slower than that loop? Actually, no. Why is this loop 60 times slower than that loop? Okay. I would venture to say that 99 out of 100 programmers can't tell you why. Okay. I would wager that if you went and asked 99, if you asked 100 programmers, you'd probably be lucky to find one who could tell you right off the bat why that loop is 100 times faster than that one. Okay. And the answer is a fundamental property of operating systems. This is what we're going to explain. Notice that there was a huge difference. Yeah, the code is exactly the same, you think. You're just writing a loop saying, read 1 byte, read 1 byte, read 1 byte, read 1 byte, and I'm going to count them. And this one says, read 1 byte, read 1 byte, read 1 byte, I'm going to count them. And yet one of them is 120 seconds versus 2 seconds. So there's a factor of about 50 or 60 here. And that really varies. This one, the fast one will always be about 2 seconds. The slow one will really vary. There's a lot more variation in this one. So I ran it a little while ago and it took 1.5 minutes. This time it took almost 2 minutes. Sometimes it runs closer to 1 minute. I think it has, it probably got slowed down because of Zoom. When we're doing this, the operating system has this extra heavy duty load on it of doing the stream to Zoom. So I think that's why before class it ran at 1.5 minutes and now it runs in 2 minutes. What would Zoom have to do with this? It doesn't affect this guy at all. It has no effect on this one. The fact that Zoom is running probably has, this number here is exactly the same as it was before class. This number changed a lot when I turned on Zoom. Okay. And on your computer at home, you could test it too. Like, I don't know if Zoom has as much, I don't know if there's a difference between me and you. Like we're both streaming, you're streaming in, I'm streaming both, out, but I'm also recording. So that puts even a little bit more burden on the computer. So, you might try running that while Zoom is on, and then afterwards when Zoom is off and see if it changes. It might change a certain amount. What's going on? That's a huge difference. An order, 50 times slower, 60 times slower is crazy. Remember, that's the difference between something taking, 2 seconds and 2 minutes. Something that takes an hour becomes something that, if this was a 1 hour program, this would be days and days. Okay. There's something really profound happening here. Okay. So the answer is these pictures. Okay. The answer is these pictures. This one's the Windows version. This is the one that's incredibly slow. And then I need to, where's the other, did I lose the other picture? Let me close. Okay, here's the Windows picture. And here's the C picture. The C picture is not complete. I want to finish it. I left it incomplete, so I'm going to draw some in here and explain what's going on. Okay, here's the Windows picture. What Windows is doing is, here's the hard drive over here. Here's my buffer. It's really just 1 byte. Okay, and I want to read 1 byte into that buffer from the hard drive. Now, as we said in class the other day, this guy does not talk to the hard drive. We're in user space. So what this guy has to do is it has to call this system call in kernel space. So this function calls that Windows built-in function, and it's called NT read file. All the functions that have an NT in front of them are what Microsoft calls their system calls. Linux has a different way of naming their system calls. Windows actually kind of clever. They took the the user space function put an NT in front of it. That was the original name of the operating system, Windows NT for new technology. So the system calls have a little NT in front of them. This function changes from user space to kernel space because it's the operating system that has to communicate with the hard drive. Okay. Now, NT read file creates its own buffer. Okay. It's not going to ask for 1 byte from the hard drive. For example, the hard drive won't even give it 1 byte. The smallest unit you can read from the hard drive is 1 sector, which is 4,000 bytes. So this kernel buffer is probably some multiple of 4,000. It's either 4,000 bytes or 8,000 bytes, maybe 16,000 bytes. And when you ask for 1 byte, NT read file will actually ask the hard drive for at least 1 sector, maybe a couple sectors, because it assumes that if you're going to ask for 1 byte, you're going to ask for another one, and you're going to ask for another one. You know, and it just assumes that it's not worth its while to go ask for 1 byte here. It's like you go to a grocery store. If you need an egg, you don't buy 1 egg, you buy a dozen eggs. Okay, you know, it's not going to go over here and just ask for 1 byte. It figures you're probably wanting more. And actually, the hard drive just won't even give it 1 byte. The smallest unit you can read from the hard drive is called a sector, and it's 4,000 bytes. It's 4 kilobytes. So it's not 4,000. It's this number here, 4,096. That's 4 kilobytes. Remember, that's 1 kilobyte. That's what 2 to the 10th is. That's our 1,000 in computers. That's 1,000. That's our 2 kilobytes. That's our 4 kilobytes. That's the sector size, 4,096 bytes. Okay. All right. So you switch from user space to kernel space. NT read file asks the hard drive to give it 1 buffer full. Okay, fills this buffer. Now that takes a long time. The hard drive's slow. So this process gets put into the blocked state. Then when the hard drive is done reading the sector, it interrupts the CPU, which puts you back into the kernel space. And then the operating system notices that this buffer is full, and it puts this program here from blocked to ready, not necessarily to run, from blocked to ready. And then the operating system goes back to whatever it was doing. So when the hard drive finishes the IO operation, it interrupts the CPU. That traps the CPU into the kernel. The kernel does the bookkeeping. It moves that process from block to ready, and then after it's done the bookkeeping, the CPU is allowed to go back and do whatever it was doing, running somebody else's program probably. Okay. Then when this program gets back into the run state, then NT read file can return. See, this thing blocked in the kernel space. So when it unblocks and then becomes ready and becomes running, it starts running in kernel mode. Well, NT read file can take 1 byte out of that buffer and put it over here, because that's all this guy asked for. He asked for 1 byte. Okay, right? Now, what happens next? He needs another byte. Remember, he's in a loop. So he asks for another byte, but to ask for another byte, he's got to go from user space to kernel space. Now, when he gets in here in kernel space, NT read file says, well, I've got a lot of bytes here. He wants 1 more, so he gives 1 more byte to this program. Okay, this program loops and asks for another byte, which means you have to go from user space to kernel space again. Well, NT read file's got 4,000 of these bytes in this buffer. So this happens 4,000 times. This thing switches from user mode to kernel mode, gets 1 byte from that buffer, and returns. Does that 4,000 times. After it does that 4,092 times, at that point, this buffer's empty. So next, when this guy asks for 1 more byte, you go here, buffer's empty. So now NT read file asks the hard drive for another sector. So that leads to an IO request. Now, at that point, this program is put into the block state. It stays in the block state until the hard drive finishes the IO request. When the hard drive finishes the IO request, it interrupts the CPU, which puts you back into the kernel. The kernel does the bookkeeping that this IO request is completed, and this process is put from blocked into ready. Then the CPU goes back to what it was doing. When this guy is run, you pick up in kernel space. So when it goes from ready to running, you pick up in kernel space. Well, now there's 4,000 bytes in this buffer, and 1 of them is given to this guy. and then that goes on over and over again. He gets 1 byte at a time by doing a switch from user space to kernel space. Okay. And every 4,000 bytes, there is a request from the hard drive for another sector. Okay. Now, why is this program taking so long? It's making 40 million. Okay. Notice that it read 50 million bytes. See, this is how many characters were read. This number here, if you put commas in it, it's 50 million. This thing did 50 million switches from user space to kernel space and back again. That's what took a long time. It's switching from user space to kernel space that took this one a long time. Now, why was this one fast then? It seems like the picture here would be the same thing. This is a 1 byte buffer. It needs 1 byte, so it needs to go over here. But it turns out in this picture, there's something hidden from you. Oops, what happened there? Oh, I want to open this. I want to open this thing in Paint and add to the picture. fread has got a little piece of magic. Well, it's actually a brilliant idea. What fread did, the people who wrote fread, their function has its own buffer. So in this picture, there would be another buffer sitting right there. Okay, and this would be the fread buffer. So there's this buffer sitting here that belongs to fread. Okay. And what fread does is it's a little bit clever. fread knows that this transition from user space to kernel space is very expensive. So here's how this flow works. Your program calls fread and asks for 1 byte. fread starts up and says, well, my buffer is empty. Okay, so at the beginning, this buffer is empty. So fread calls ntread file and says, give me a buffer full. Now remember, this program asks for 1 byte, but fread's kind of clever. fread calls ntread file and says, give me, it makes this buffer, I should have put it, it makes this buffer, you can, by default, I think that buffer is, well, I think it's 8 kilobytes by default. I think this buffer is 8 kilobytes by default. Okay. I don't know how big this kernel buffer is. I'm guessing it's 4 kilobytes, but it's going to be some multiple of 4 kilobytes. And in this one, I'm pretty sure, I think this one defaults to 8 kilobytes. Okay, so fread, you asked for 1 byte from fread, but fread says, well, I'm going to actually ask the kernel for way more than that. I'm going to ask the kernel for 8,000 bytes. Okay, so that makes a system call to the kernel. The kernel's asked for 8,000 bytes. The kernel has its buffer is empty. So the kernel has to ask that from the hard drive. Again, we said this many times. That takes a long time. This process is put in the block state. The hard drive does its work. When the hard drive is finished, it signals, it interrupts the CPU. The CPU traps to the kernel. The kernel does the bookkeeping to realize that this buffer has been full. It puts this process in the ready state. Then the kernel goes back, then the CPU goes back to what it was doing. When it's finally time to run this process again, this process restarts from in the run state in the kernel space with a full buffer here. Okay. Now, ntread file was asked by fread for a full buffer. So all this data is copied into here. Okay. So all this is copied into here. Now, finally, fread says, now I got your byte for you. So fread returns 1 byte to here. Now things get interesting. When this thing asks for another byte, it calls fread, and fread says, I have a byte for you, and returns right away. Then this thing asks for another byte from fread, and now you can go through 8,000 bytes where there's no IO and no system call. Every time my program asks fread for a byte, fread's got the bytes in its buffer in user space. It's part of this function. The person who wrote this function he buffered the IO. So he's got this stash of bytes, and every time you ask for a byte, he gives it to you from his stash. Now, when this thing empties and you ask for one more byte, then fread makes the system call. But notice he only makes a system call for after you've asked for 8,000 bytes. So at some point, fread makes a system call. Okay, then the whole process goes. The hard drive will do this program becomes blocked. The hard drive does the work. The hard drive copies the data into this buffer. When the hard drive is done, it signals to the operating system that it's done the IO operation. This process is moved from the block state to the ready state. When this process finally gets in the run state, it starts up in kernel space, and NT read file can then copy this buffer into that buffer and then return to fread. And then fread is ready to start feeding bytes over to here. Okay, so if we go back to our code, the Windows program made 50 million system calls. Every one of those was a system call. Now, some of those system calls only got 1 byte at a time. Remember, many of those system calls were, you made the system call, the byte was right there, so you returned. So it was a system call with no IO operation, but you still had to make a system call. So the Windows program made 50 million system calls, and it made a certain number of IO calls, however many times you had to fill this kernel buffer, that's how many IO calls it made. But the IO calls are not really what's bothering us. What's bothering us is the 50 million system calls. What does this guy do? This guy makes 50 million function calls from here to here. There's 50 million function calls from here to here. Now over here, there's 50 million function calls to fread and 50 million system calls to NT read file. Here, there's 50 million calls to fread, and that's about it. There's only a few system calls. Every 8,000 bytes, there's a system call. So this thing is doing 1/8,000th of the system calls that this one is. Okay, where this one does 8,000 function calls and then needs to do 1 system call, this thing does 8,000 function calls and 8,000 system calls. The system calls return with 1 byte at a time. Just like the function calls here return with 1 byte at a time, over here, the system calls return with 1 byte at a time. But that system call itself is, the rule of thumb is a system call is about 10 times slower than a function call. It depends on the operating system, but a system call is at least 10 times slower than a function call. You can't think that system calls and function calls are equivalent. System calls are profoundly different because they switch from user space to kernel space. So back in code, every one of these is a system call. These are mostly function calls, and they only turn into system calls every once in a while. Like for every 8,000 function calls, you get 1 system call. You essentially can forget the fact that this is even a system call because it doesn't lead to a system call very often. Okay, but this one is 1-to-1. Every time you make this function call, you're actually making a system call. Okay, now let's show that this is what's going on. Okay, let's start changing the buffer sizes. What happens when we change the buffer size? Okay, so let's just change the buffer. Let's double the buffer. Double it to 2 here, and double it to 2 here. Okay. In this one, that's gonna have the number of function calls. Okay, so instead of making 50 million function calls, we're gonna make 25 million function calls. That does not speed up my program by a factor of 2. It hardly makes my program any different. So let's try that. Okay, so we're going to cut down the number of function calls in half. So go over here to the program. I'm going to run the program now. So I need to recompile it. So I'm going to recompile. That's the C. I want to compile the C library one. Okay, and run the C library one. Okay, so there's the C library one. I'm going to run the C library one. I've cut down the number of function calls. Okay. Oh, actually, it did almost double the program. It did get, it got about half this. made half as many function calls and did almost get half as fast. Okay, see, because that made it, but it was, it was a 1 second improvement in speed because it was already only 2 seconds long. Now, what about the other one? Okay, now do the same thing for the Windows one. This is going to cut it from 50 million system calls to 25 million system calls. So compile the Windows one. There's the Windows one. And run the Windows one. Now, this one should cut down from about 2 minutes to 1 minute. It should become approximately twice as fast, but cut from 2 minutes to 1 minute. Now, as we increase the buffer sizes, this one, it'll, like if we go from 2 to 4, it'll get faster again, but at some point it's going to stop becoming faster, because at some point the number of system calls is not as important as the I/O itself. So I forget where, somewhere in here it stops becoming faster. Whereas this one, as you keep cutting down the number of system calls, it just keeps getting faster and faster and faster and faster until you get to about here. Then it's running, it's making about as many system calls as this one is. Okay, so see there, see, cut from 2 minutes to 1 minute. Okay, now do it again. Let's go from 2 bytes to 4 bytes. And from 2 bytes to 4 bytes here. One of them we're cutting in half the number of function calls. And the other one we're cutting in half the number of system calls. So here is compiling the C library one. And I'll run the C library one. There's running the C library one. See, now it ran in 3/4 of a second. So it cut down in half. Now compile the Windows one. Run the Windows one. Now it's going to take about 30 seconds. Now, it's this point, you look like a genius to your boss because you just cut the runtime of a program in half by changing a number from 2 to 4. Okay, and people are going, how can you be so, how can you be such a clever programmer that the difference between 2 and 4 made your program twice as fast? And notice how it's see there, it took 30 seconds. Notice how a tiny change in a program can double the speed of the program. If you understand operating systems and you understand these pictures, system calls versus function calls, you can actually answer people's questions. When people say, why is this program so slow, but this other guy's program over here is so fast, you can start explaining what's going on. And the world is full of stories where companies actually were doing literally dumb things like this and not realizing that they were just doing massive numbers of system calls. I mean, there are real life stories of companies having code written just like this, not realizing that this and this don't behave the same, and you can't just treat them as one-to-one replacements. You can't just replace that with that. If you saw this in Google and you say, I'm going to replace it with this, it's not the same thing. If you're just Googling around and you say, oh, I can change this function to this function, and you think, well, they look the same, they do the same. It turns out they don't do the same thing at all. This one's buffered and this one's not buffered. Okay, this one's not buffered, this one is buffered. And that makes all the difference in the world. And and if you go to the Linux version, the Linux one is unbuffered too. The Linux one acts just like the Windows one. This is an unbuffered system call. So that will make 50 million system calls, just like the Windows version would. That is the low-level operating system read, and so it's not buffered. Okay, so it would act just like the Windows one. Okay, now, but if you read if you go and read the documentation from here, there's no mention of system calls in the documentation. They don't hint at it. They don't hint that this thing is profoundly different than this. And if you read the documentation from this, it hardly mentions the buffer even. If you actually go read the web page for this function and the web page for this function, there's very little clue that they're profoundly different. That they probably do mention somewhere that this thing's buffered, but they don't really explain it, what that means. It's up to you to know what it means to say this thing's buffered. And when they say, now they're both buffered because they both use a kernel buffer. But that's part of, the system call. The system call has this buffer to hold what it gets from the hard drive. So they're both buffered, but they're both buffering the IO from the hard drive. But one of them is buffering the system calls. One of them is buffering in user space. The key is fread's got a user space buffer. Okay. Now, there's a bunch of things we can do here. Like, if we keep increasing the size of the amount of data we want from this thing here, we make fewer and fewer system calls. So at some point, when we increase the buffer size here, like I'll go up here. Let's just go all the way up to the maximum and go up here all the way up to the maximum. They will be pretty much the same now. At this point, they'll have caught up with each other because they're now pretty much doing the same thing. In fact, it might even be the case, there's a potential now for the Windows one to be faster than this one. When Windows is asking for 4,000 bytes at a time, it makes a system call, gets 4,000 bytes, and comes back here. Then makes a system call, gets 4,000 bytes, and comes back here. Whereas this guy, now, he makes a function call and gets 4,000 bytes from there, but the 4,000 bytes needs to make a system call. Suppose this buffer's 4,000. So function call to get 4,000, system call to get 4,000, function call to get 4,000, system call to get 4,000. Here, it's all just system calls. So there might actually be a little, it seems like there's one fewer step here. Because here you just go system call, get the data, system call, get the data. Here you go function call, get the data, copied here. At this point, I'm not sure. They're either going to be the same speed, or maybe this one will even be maybe a tiny bit faster because it doesn't need to copy. For example, it doesn't have this intermediate buffer that needs to copy into. So let's try it now. We're not making the programs the same. We're just making this guy grab essentially a large chunk from this buffer at a time. This guy has still got this one here. So when this guy asks for 4,000 bytes, he asks for 4,000 bytes from here. More than likely, this one gets the 4,000 bytes from there. It might be that it does every other one. Like if this really is an 8 kilobyte buffer, this one would ask for 4,000 bytes, get them, ask for 4,000 bytes, get them, ask for 4,000 bytes. It goes up here, gets 8,000 bytes, then gives 4,000, 4,000, then goes up here, gives 8,000. But that would still be half as many system calls. So it kind of depends. Okay, this one would be making more function calls, but it might still be making half if this thing's an 8 kilobyte buffer. Okay, let's try it. Compile the Windows program. Well, let's do the Linux one or the C one first. So compile the C program, run the C program. Okay, 0.2 of a second. Okay, it's pretty fast at this point. And if you increase the buffer size, it won't get any faster. At this point, that's pretty much dominated by how long it takes to actually do the IO. You're not going to get this much faster than that. Okay, now about the Windows one. Compile the Windows one. Now run the Windows one. And it was faster. Well, look, it got a 1/10 of a second. Okay, 100th of a second. Yeah, the Windows one actually became faster now. Okay, there's the C library one. It's running at 0.1, and there's the Windows one. It's running now. Excuse me. Now the Windows one is running much faster. My guess is the Windows one is now faster because it doesn't have to do that intermediate copy step. So, okay. So, but you have to notice that you might say, oh, I should have been using Windows all along, but you have to know to make that buffer size real big. You have to know that you better make that buffer size real big in this case. Notice that to get good performance here, I had to have a big buffer size. To get good performance here was, oh, this is the Windows one. In the Windows one, to get good performance, I had to have a big buffer size. In the Linux one, in the C library one, I didn't have to have a big buffer size. Now, there's an advantage to this C one, and this is the following. In another class, I do this example, and I will expand on it a little bit more. Here's the problem. Suppose I want to ask you is how many letter, this is kind of a, might be a dumb question, but how many letter Z's are in that file? Okay. I want to know in this file, how many times the letter Z appears? Okay. All right. Well, how do you do that? You have to step through the file one byte at a time. Okay. So you have to step through the file one byte at a time and look at each byte. Okay. So this code is set up to do that. It was set up to do that. Read one byte at a time and look at it. And then I could just count, I could put an extra line of code here that says, well, if the byte is a Z, count it. Okay. Instead of counting every byte, I'd only count the bytes that were a Z. Okay. Now suppose but this is fast. Okay. Now over here, I want to find the Z's. Well, to make it fast, I need to read 4 kilobytes at a time. But now I've got a buffer full of letters. So now I have to write more logic. Instead of just checking the variable I got, I now have a buffer full of letters. I've got to write more code in here that steps through the buffer and looks for Z's. Okay? Because I grabbed bufferfuls of data and I want to count the Z's in the buffers, I have to have a loop inside of a loop. Whereas this one, the code's much simpler. This is not a trivial example. It turns out that this is a ubiquitous problem. Buffering, like I do here, like here, by grabbing large buffers, I actually make my program harder. I can show you much more profound examples in this, where if you read data in large buffers, it becomes tough to go through the buffers and look for what you need. If you read in smaller chunks like this, it can make your logic way simpler. But you need somebody else to do the buffering in that case. Somebody has to do the buffering. You can't do a gazillion system calls. You can't just keep doing millions of system calls. Somebody's got to do the buffering. That's why this was set up this way. This was set up this way for the purpose that they do the big buffer, you do the little buffer. The little buffer makes your logic easier. The big buffer makes the program faster. They hide the big buffer, you make it a little buffer. So a classic example of this is when you want to read a text file line by line by line, right? You want to read one line at a time from a text file. But one line's 10 bytes long, one byte's 50, each line is a different length. If you have to do your own buffering, you have no idea how long the lines are. So if you want to read one line from a file, you have to grab a whole buffer full, search the buffer for the end of line character, and then pull out one line from it. Then search your buffer for another end of line character, pull one line of it. You have to write lines and lines and lines of code to do that. On the other hand, over here, there's a fread that reads one line at a time. And it has a buffer. And what it does is it does the big buffering, and then it'll read from the big buffer one line at a time for you. You write simple logic, and it does the buffering. If you think you're going to do everything, if you want to do your own buffering and your own logic, you end up writing way more code. Okay? You have to do buffering because you can't just first of all, you can't ask NT read file for one line. The hard drive doesn't know anything about lines. NT read file doesn't know anything about lines. The only way you can find one line of text is you have to read a buffer, then look in the buffer for the /n character, and then that's the end of the line. Somebody has to do all that logic. If you're going to write your code using the read file, you've got to write all the code for all the logic. Okay. On the other hand, if you use a C library function, they'll build they'll put the buffering in their function for you. They'll do the buffering. The C library functions all do buffering for you. Then you have small buffers here, like a line buffer, And then you can say, get me one line from that buffer. Get me one line from that buffer. When that buffer is empty, then they'll do the system call to fill their buffer up. They'll do the line buffering logic for you. And then you could do simpler logic here. Count lines, look, analyze lines of a file. Almost all text files are analyzed one line at a time. That's what this is set up to do. Okay. And they hide the buffer from you. Okay. You can be as fast now, you can be as fast as them, but you have to write more code. But to be as fast as them, you have to realize that you've got to do the buffering. You've got to ask for large amounts of data at a time. And then you have to process the buffers in your own code. That's error prone, very messy. You know, you're way better off using library functions. And you might ask, well, why doesn't Windows give you better system calls? Why doesn't Windows give you a system call that lets you ask for one line from a text file? The answer is, why would they keep writing multiple system file? Why would they write lots and lots of low-level system calls when you can write library functions that use one simple system call? The whole point is they want you to use this library. Okay. This function here was really meant for people writing device drivers or people writing databases or real low-level code. The only people who should be doing their own buffering are people who really, really, really know what they're doing. Okay, so if you don't need to do your own buffering, you should never do your own buffering. You should use these functions that do the buffering for you. Okay, but you have to understand how this is working. First of all, if you see somebody doing this, you have to understand what it means. Okay, why if I tell you you should never do this, then why teach you it? Well, first of all, you may get the job where you're supposed to write this because you may be working on low-level code. You may be working on a web server or a database server. You may actually be doing that low-level code, or you may actually be working somewhere where somebody kind of either foolishly or just incorrectly wrote a low-level function call when they shouldn't have. But then you have to recognize it and know that it's a problem. If you see a low-level function call where it really doesn't belong, you have to realize, well, that causes system calls. That could cause huge performance problems. You could fix it by juggling the buffer size, but that may make your logic way more complicated. You could also fix it by just using a library function. Okay. Now, here's another thing that's a little bit interesting. If you go back to the C library function, they'll let you turn off that internal buffer. See that line of code that's commented out? It turns off that buffer in here. It disables it. Okay. If you go here, now let's go back. Okay. So put this back at 1 byte. Remember, this was fast like this. But now turn off their internal buffer. This is set buffer on standard in to see that NB? IO, no buffer. Okay? See, you can actually read these cryptic little things. That's an IO symbol, and it's a symbol that says no buffering on a file. Okay? So this is a symbol that says on IO, I want no buffering on my file. Okay? Use that symbol in this function call, and you're turning off buffering on that file, standard in. I do not remember what this guy does, and I do not remember what this one does. You'd have to look them up. I don't remember what they do. But turn off the buffering on standard in. Okay, now that essentially disables the use of that buffer. So it makes this function act exactly like this one. They now act exactly the same. Okay, they now a call to fread is a system call to ntread file because there is no internal buffer. So just check that, run the now. So now again, this is something that somebody could put into their code by accident. Somebody might, or maybe it was in there and it was, it needed to be in there 5 years ago and it doesn't need to be in there now, but nobody forgot to turn it off. Weird things can happen in people's code bases, but that thing has profound effect. It's going to turn off the buffering. So let's go here. And now we're back to a 1 byte buffer. This was fast. Remember, this ran in 2 seconds with a 1 byte buffer if it had internal buffering. Now I'm going to compile it without the internal buffering. Actually, I don't want to wait that long. I'm going to do 4 bytes. Okay, we'll see. If it's like the Windows version, at 4 bytes, it took about 30 seconds to run. Remember, because that was 1/4 the system calls. So this should, I think this one should run, if it's going to be like the Windows one, without buffering and a 4-byte buffer, it should make it's about 12 million system calls and be about 30 seconds. So compile it. See, where's my compile command? That's compiling. There's compiling the C library one. Okay. Now that's compiling without the buffer, without the internal buffer. Now I'm going to run it. Time this C standard library function. Okay. Should be roughly 30 seconds. Watch pots never boil. Okay. We'll see. There, 30, right on the button, 30 seconds. Okay. So this code acted exactly like this code if you turn off the buffer. If you turn off the buffer. Okay. The buffer is really profound. You know, this picture really is the key to so much in this. This picture is the key. That user space buffer, it's one of those secrets that not enough programmers know about. Okay. Where do you learn about this stuff? The only place where this is taught is usually in an operating systems class. Unfortunately, not all operating systems classes go this low level. A lot of operating systems classes just talk about the theory of schedulers. And then they don't even talk about some of this nuts and bolts stuff like oh, they'll talk about system call but not show you how, oh, it really matters. You really need to really pay attention to system calls because it has huge effects on your code. Now, there's another kind of course that's taught in a lot of schools called systems programming. And what we're doing is I'm trying to blend a systems programming class with an operating systems class. So I think you really should have both. So there is this topic called systems programming that's it's very closely tied to operating systems. The systems is pretty much operating systems. Systems programming is like learning how to write web servers and database servers and how to interact with the operating system. And many schools have a course in systems programming, and a lot of schools blend systems programming in the operating systems course. And that's what we're trying to do here. The textbook we're using is really an operating systems textbook. It's not a systems programming textbook. And I wish I could find a good book that blends operating systems with systems programming. I haven't found one. All the books I know of are either hardcore systems programming textbooks or hardcore operating systems books. It seems weird. I think somebody should write one that's more of a blended book. So our textbook is much more operating systems, but these homework assignments and like what we're talking about here, this is hardcore systems programming. How do you understand how do you understand these two pictures? How do you explain like why the same 2 lines of code can be 1,000 times, well, this 2 lines of code can be 100 times slower than this 2 lines of code, when logically they just seem to be doing the same thing. Yeah. And how did this line of code have such a profound effect on my program? If you don't know if you don't know this picture and the idea of interrupts, system calls, kernel space, user space, you can't explain it. And then the bottom line is a function call doesn't take very much time. A system call is slow. Calling from user space to kernel space is slow. Programs need to optimize how many times they switch from user space to kernel space. That's what buffers are for. But now you also need to optimize how often you do I/O. That's what this buffer's for. This buffer is optimizing I/O. This buffer is optimizing system calls. The bigger this buffer is, the kernel buffer. The bigger the kernel buffer is, the fewer I/O calls you make. Why don't you make this buffer huge? Make it monstrously big, 1 gigabyte. What's wrong with that? So every time you ask for file, you just ask for the whole file. Why not just make this buffer huge? That'll be the last question. Anybody have a question? Like, what would be this? Why not? Then you make almost no IO calls.
Could it be
It takes up too much RAM.
Yeah, if every process had a huge buffer, you wouldn't have room for them in RAM. Okay, so that's one problem. First of all, you just run out of RAM. Now, think of it. What else is bad about that? What else is bad about just saying, well, give every process a huge buffer? There's another thing that's kind of bad about it. Okay, how big should my buffer be? Say I make it 10, I'll make it 100 megabytes. Is that a good, so I'm going to make this kernel buffer 100 megabytes. Suppose I have a lot of RAM, and okay.
Could it overwrite memory from somewhere else in the?
No, that's the whole, no, that I have enough memory to hold this 100 megabyte buffer. So, I mean, I can give everybody a 100 megabyte buffer. Every time I do an IO operation, I grab 100 megabytes. If there is like if it's a 50 megabyte file, I would just read the whole file. If it's a 200 megabyte file, I read half of it. But my buffer is 100 megabytes.
Is it because the IO operation is slow?
Well, they are slow. That's why I'm buffering them. So that you just do them all at once. Say again, what?
If you're taking a lot of data at one time, is that the bottleneck?
No, that actually speeds things up. That's the optimization. Grab as much data as you can at once. It's faster that way. What's wrong with a 100 megabyte buffer? Now, like the first issue is a good one. I may not have room to give everybody a 100 megabyte buffer, but suppose I do. Suppose I don't have very many products. Suppose I have the room to give everybody a 100 megabyte buffer. It's still not a good idea. It does optimize speed. It does optimize IO.
If your operating system gets compromised, you lose all your files.
No. Okay, think of it this way. Suppose this buffer is 100 megabytes, and this is a 50 megabyte file. So I'll always read 50 megabytes from the file into this buffer. So every time I do an IO operation, I'm grabbing upwards of 100 megabytes.
If the file's 50 megabytes and you're using a 100 megabyte buffer, aren't you just wasting 50 megabytes?
Yes, but suppose I've got the room and I've got that room in my hard drive. So I'm my memory. I have that memory. That's called internal fragmentation. Yes, I'm wasting space, but there's still a slightly more subtle problem. I'm wasting space. I'm also wasting time. Where am I wasting time? I got a 100 megabyte buffer and a 100 megabyte file. I need to read some data from the file. So the system call reads 100 megabytes from the file, reads the whole file every time. That's super. That's kind of efficient, but in a way, it turns out to be not right.
Because the hard drive's so slow.
No, that's why you're optimizing IO. Since the hard drive's slow, it's like to go to the grocery store. You see those people pushing 2 carts in the grocery store because they're just going to make one trip to the grocery store, get as much stuff as they can in one trip, and they're optimizing their time. So they're pushing 2 carts in the grocery store because that's the optimal thing to do. Grab everything you can in one trip. So
the limit of your FRead buffer is only 8K.
No, we're making it. No, but then there'll just be a lot. That'll just be a lot of transfers from here to here. I'm trying to optimize the IO from the hard drive. So I make this 100 megabytes. So I don't do that many IO. I do optimal IO operations. I just grab everything and pull it in here. Okay, you have a 100 megabyte file and a 100 megabyte buffer. But what if you only need the first 10 megabytes of the file? What if it's a log file and you only want to read today's logs? You don't want to read all the logs that go back the last 5 years. You'd only want to read the first 10 megabytes of the file. But if your buffer is 100 megabytes, you're going to read the whole file all the time. You're actually reading, having too large a buffer has you read data you don't need. See, too small a buffer, this is one of the profound systems programming trade-offs. The buffer's too small, you have to keep going back for more. If you use too small of a cart at the grocery store, you have to keep going back to the grocery store. If your buffer's too small, you have to keep going back too often. If the buffer's too big, you start reading data you don't actually need, and you're wasting time reading data you don't need.
So does that mean if you have too large of a buffer, that means it's sort of like a minimum amount of time that you have to spend?
Yes. Yeah, your minimum amount of time is to read that whole buffer. You're forcing everyone to read 100 megabytes of data all the time. So you're making that the minimum amount of data to read. But 100 megabytes would be a ridiculous minimum amount of data to read. Okay, so there's this trade-off. The buffer's too small, you have to keep going back. If the buffer's too big, you're reading more stuff than you really should be, and that's wasting time. Where's the sweet spot? How do you think Microsoft figures out the right size for buffers?
They see how big the file is.
Well, they know. Yeah, no. This is something you have to decide in the. Yeah, you have to decide how big this kernel buffer is. That's something that Microsoft decides. Should they make that kernel buffer 8 kilobytes or 8 megabytes or 100 megabytes? Too big, and you're wasting time reading data you don't ever need. Too small, you have to keep going back to the I/O. Too big, you read data you don't need. Too small, you have to keep going back and do more I/O operations. How do you find the optimal size of the buffer? The answer is Microsoft runs experiments. They treat it as an experimental science. They modify the size of that buffer, run Windows for a few days, change the size of that buffer, run Windows for a few days, performance analyze, try to figure out where the sweet spot is. Essentially as an experiment, trial and error. Then they try to analyze it mathematically, which is usually kind of hard. And basically it ends up just being an experiment. So like buffer sizes of 8 kilobytes have historically turned out to be seemingly like a good idea. So it's more or less trial and error. They make it bigger, and then they just see how do programs run. Does the operating system get faster or slower? Is the operating system running better or worse? If they make the buffer too big, they start seeing the performance degrade. If they make the buffer too small, they see performance degrade. They try to find a sweet spot. It actually literally becomes an experimental science. They profile their programs. They run their programs millions and millions and millions of times with different sizes of buffers and try to figure out where's the right size. Okay, it's kind of interesting. It's done as like an experimental science. Okay, we've gone over. We should quit now. Okay, and I'll put these pictures. I'll put these two pictures up. Yeah, these are the pictures that I should have done last week. That see, the key is to compare the Windows version with the C version because the C version's got this extra buffer. Okay, so on Wednesday we'll start talking about scheduling. So we're ready to move to the next chapter of the book to start talking about the theory. Now we go back to theory. So we've been doing hardcore practical stuff, looking at real code here and seeing how and analyzing it. And then on Wednesday we'll go back to theory stuff. Okay. Anybody any last second question? Any last question? Look at this stuff over. It's fascinating if you like low-level stuff. Yeah, it's something that would interest people who really like low-level programming, but it's something that everybody should be aware of. Okay, so I'll go ahead. See, I have to find the button. Oh, there. I'm going to stop sharing. So meet again on Wednesday. Bye.